There are 6 known adsorption isotherms today. That is type 1, as shown in that diagram, type 2, type 3, type 4, type 5, and type 6. It's clear that type 1, type 2, and type 4 are similar in that they have got a sharp turn there, and there, and there. Similarly also, type 6 also has a sharp turn. We can also see that type 4 and 5 have a similarity in that they have got a hysteresis there and a hysteresis there. Now these are a product of plotting amount adsorbed in X against partial pressure, P over P naught. P naught is the saturation vapor pressure of the adsorbate at the given temperature. Now let us analyze each and every one of these isotherms. This is according to the classification of adsorption isotherms by BET. Brunauer classified adsorptions into 5 isotherms. Most of them were characteristic of the 3 processes in physical adsorption, physisorption. 1. Monomolecular adsorption. 2. Multimolecular adsorption. 3. Condensation in pores and capillaries. Right, let's look at type 1. A very good example of type 1 adsorption isotherm is the adsorption of ammonia on charcoal. This adsorption is characterized by a rapid in amount adsorbed at low pressure reaching a limiting value, and adsorption is limited to a monolayer. What do we mean by this? It means one molecule per site covering the whole surface. This is typical of chemical adsorption or chemisorption. It can also be due to physisorption by solids with fine pores. For example, nitrogen on microporous carbon. Let's now look at type 2. A good example of type 2 adsorption isotherm is nitrogen on silica gel at 77 K. Multi-layer physisorption on non-porous solids, sometimes described as the sigmoid isotherm. It has a clear point B representing the completion of a monolayer. Physisorption on micropolar solids is possible. In this case, point B represents both monolayer adsorption on the surface as a whole and condensation in the fine pores. The remainder of the curve represents multilayer adsorption as for non-porous solids. Let's jump over to type 4. A very good example of type 4 adsorption isotherm is benzene on iron 3 oxide gel at 320 K. It levels off near the saturation vapor pressure. It's considered to reflect capillary condensation in porous solids. That is, solids with large pores. the effective pore diameter is 2 nanometers to 20 nanometers. The upper limit is governed by the total pore volume and is named after Gavage as the Gavage volume. Right, let's go to type 3, which has got some similarities with type 4. Type 3 is exemplified by adsorption of bromine on silica gel at 352 K. And type 5 is exemplified by water vapor adsorption on charcoal at 373 K. In these two, there is no rapid initial intake of sorbate as in 1, 2, and 4, and 6. This occurs when the adsorption force is very small. That means the interaction between the adsorbate and the adsorbent is minimal. These are rare. Right, let us now go into the theory of adsorption, starting with the simplest, that is the Langmuir model of adsorption. We already know that adsorption is an equilibrium. Okay, let us assume that there exists a dynamic equilibrium between the adsorption rate, which is a Kr1, P into 1 minus theta, and the adsorption rate, which is Kr2 theta. If that's true, then theta can be equal to Kr1 into P over P naught all over, open bracket, 1 plus Kr2 into P over P naught, close bracket, close bracket. Here, Kr1 is the rate constant for adsorption. Kr2 equals the rate constant for desorption. Theta is described as the coverage. This is the fraction of the surface covered by the adsorption. So it varies from 0 to 1. If we put theta is equal to nx over nm, and b is equal to Kr1 over Kr2, where nm equals the moles of adsorbate to fill a monolayer, and nx is the number of moles of adsorbate at any pressure P, then the linearized form of the equation becomes P over P naught all over nx is equal to 1 over B nm plus P over P naught over nm. Consequently, a plot of P over P naught over nx against P over P naught should give a straight line of slope 1 over nm and intercept 1 over bnm. Consequently, nm may be evaluated from the slope, while b is obtained from the intercept. Nm is related to the specific surface area by nm is equal to a all over NaAm 10 to the minus 15. Where A is the specific surface area, Am is the cross-sectional area of the molecule. Now, the Langmuir model is based on assumptions. In the deriving of the foregoing equation, Langmuir assumed that 1. Adsorption stops at a monolayer. 2. Adsorption is on specific sites, i.e. is localized. It's not anywhere, it's on specific points. 3. The heat of adsorption is independent of the surface coverage. In other words, the adsorption sites are equienergetic. Now, this all looks wonderful, but really, is this the case? So let's look at the criticisms of this model. The heat of adsorption is independent of coverage. This cannot be because we have sites inside the pores, at the edges, at the flat surfaces, and in crevices. The adsorption force field for all these and many others not mentioned must surely differ. Hence, delta H adsorption for each of them will differ. Two, the cross-sectional area of the adsorbate molecule will differ with orientation of the adsorbate molecule, which is assumed to be spherical. Hence, the area obtained from different values will differ. Let us look at examples of molecules frequently used. Nitrogen, for instance, is N triple bond N. Ethanol, CH3, CH2OH. Would you consider these two molecules to be spherical? I don't think so. Consequently, the area you obtain will depend on the orientation of the molecule on the surface. If it's lying flat, then the cross-sectional area of the molecule should be that of a flat molecule. If it's lying at the end of the molecule, then the cross-sectional area will depend on the cross-sectional area of the end of the molecule.